Okay, let's go ahead and do this. This first question. What am I looking for in this problem? So I'm looking for a number that's got degrees Celsius as my answer. We okay with that? So I'm going to use the railroad track thing and come up with a degrees Celsius answer. I've got heat. We're looking for calories. We're not looking for degrees Celsius. We're looking for something that's got calories in. And I have one thing up there with calories. So some amount of heat is going into this aluminum, and the aluminum's temperature is going to go up. Do I care what the aluminum's initial temperature is? Yeah, I don't care what the initial temperature is. I only care what the difference between it and the final temperature are. So that means that the initial temperature and the final temperature are not important. They're only important in the fact that I can figure out what the change is. If I add this amount of heat to aluminum at any temperature, its temperature is going to go up whatever we calculate. So how much is its temperature going to go up? Uh, 100 is my final temperature. No, it's not. It's 110. 110 is my final temperature. And then my initial temperature is 3. So I get 107. Okay. So I know this thing is going to go up 107 degrees. Now I can use all of this information to calculate my the heat that's going to go into this. And so since I've got a unit that's got calories in it, or a number with calories in it, I'm gonna put 0.22 calories per gram degrees C. I'll start the railroad track off like that. And then I'm gonna use that change in temperature number I calculated, and I'm gonna put it in the numerator. That way I can get the degree C unit here to cancel out with the degree C unit there. And then 75 grams will cancel out with the gram unit down there. And what do we got here? 0.22 times 107 times 75. So I've got 1765.5 calories. And what should I report for my answer? $1,800? Are we okay with 1,800? Why 1,800? 2 sig figs, 2 sig figs, 2 sig figs, 3 sig figs. So I can only put 1,800 down. I can either write 1,800 calories or 1.8 times 10 to the third. Either one of those will be fine. Okay. So I said this one was tricky. And I looked through the homework, and it only looks like a couple of people figured it out, which is fine, except nobody else messaged me, or nobody else posted any questions on the forum or any of that kind of stuff. So you really need to...
So are we allowed to post questions from this homework on the forum?
Yeah.
I was under the impression it had to be a question from this book.
Yeah, but you're not prohibited from posting anything else you would like. I definitely want a question from the homework, but if you have another question about anything, you can still post it.
Okay.
There's no, you're not banished from. I've had people post a dozen times a week asking questions, and yeah, take advantage of that. Okay, so there's a couple little tricky things with this. I think the easiest thing to do, or to help out with this, is just draw yourself a little picture. So what I've got here is a relatively cool container of water and a relatively hot container, or a chunk of lead. So the lead's going to go into the water, and what's going to happen to the water's temperature? It's going to go up. And then the lead's temperature? It's going to go down. Do you know, tell me why the water temp doesn't keep going up? And when does the lead's temperature stop going down? So there's the very first key to this question, that the lead's temperature and the water's temperature, final, they're going to be the same number. We okay with that? So I need to know what the lead's initial temperature is, and I can get that by using the change in temperature stuff, right? So if I know what the change in the heat was and I know what the final temperature is, I could just do some subtraction and figure out what the initial temperature is. So ultimately what we're looking for is we just want to be able to solve that equation for the lead. Well, we don't have enough information right off the bat to figure out what the change in temperature is, but we can figure out some other stuff. So what, given this information that we have here, what can we calculate?
The heat for water.
Yeah, we can figure out how much the water's heat went up, right? And that's going to be important to us in a sec, but let's do that first. So it's the specific heat is 1 calorie per gram degree C, and I need to cancel out the grams for the water, and that was 175 grams, so that'll go there. And then I've got I got to get rid of that degree C. So in this equation, what degree C do I care about? I only ever care about the change. When I'm talking about specific heat, the definition should be how hard or how easy it is to change something's temperature, and so I only ever care about the change. So it's at 11 and it goes to 22, so then its change is 11. So I'll go ahead and I'll put an 11 degrees Celsius up here and cancel that guy out. And so then I've got 11 times 175. And it's 1,925 calories. Great. So then the next little tricky part of this question has to do with this 1925. What do I know about that 1925 calories? Very good. So the water took this much. Where did it come from? It came from the lead, so that means the lead gave it away. But the lead gave it away. So tell me what the Q is for the lead. It's negative 1925 calories. We okay with that? It had heat, it gave heat away. So its actual heat number is less than what it started with, so it gave that away. So I'm gonna have to write negative for that. Okay, so what I'm trying to calculate again is that, that temperature final there. What I have is the amount of heat that the lead lost. I know what the final temperature of the lead is, and I know what the mass of the lead is, and you guys could look up the specific heat for the lead. So what was the lead specific heat? 0.038 calories per gram degree C. So what I need is that degree C there in that specific heat, because that degree C is the change in the temperature of the lead. So I'm going to write grams degrees C divided by 0.038 calories. Okay, so why did I write it upside down like that? Is that okay? I can totally write, because this is just a ratio, and so I can write it upside down, right side up, however I want. And I did it because Camille said I want that degree C part. So I put the unit that I want in the numerator, because that's where I want it to be. And now I need to get rid of the grams and the calories. So I'm going to go ahead and write 75 grams down here in the denominator to cancel out the gram unit. And what am I going to write? How am I going to cancel out the calorie unit? Negative 1925 calories right here. And so the calories cancels out. So then I've got negative 1925 divided by 0.038 divided by 75. And I get negative 675 degrees Celsius. Is that my answer? No. So what is that number? So the lead's temperature actually drops 675 degrees. Okay, So then I can go ahead and plug it into this equation up here. And so I've got negative 675 degrees Celsius is my change. My final temperature is what I'm looking for. And what's my initial temperature? I'm sorry, I'm looking for my initial temperature. What's my final temperature? Yep, it's 22 degrees Celsius, and I'm looking for my temperature initial. So algebraically, I'm just gonna, temperature initial is equal to 22 degrees Celsius plus 675 degrees Celsius. So 697 degrees Celsius, is that right? Yeah, 697 degrees Celsius. Looks like I only have two significant figures, so my answer will be, what is wrong with me writing 700 degrees Celsius? Why is that not great? What does that look like for sig figs? 1. How many do we get to put? 2. So the best way to write this would be 7.0 times 10 to the second degrees Celsius, because then the 7 and the 0 are known to be significant figures. That one was fun, right? You want to see lots of questions like that on the exam? That won't happen. You only get super complicated, crazy stuff at homework because I'm expecting you to talk to each other and look stuff up. Okay, so why should you not get super excited about seeing the sign that says 125? Yeah, because it's kilometers per hour, right? And it's 40% less. I saw some video yesterday of some guy videotaping another guy. He's a passenger in a Lamborghini, and they were driving like 333 kilometers per hour. So that's fast. That's over 200 miles an hour. And the end of the video was, I don't know what happened. The guy wasn't really paying attention. He just drove off of the road into the ditch on the side. There wasn't really anything left of the car, or the people for that matter. But the phone survived. So they had the video from the accident. But it was basically just charred nothingness. It was sad. They were all like super excited when they hit 333 kilometers per hour, and then like 10 seconds later, there was no car. Okay, so I want to convert this 125 kilometers per hour into miles per hour. So I'll go 125 kilometers per hour. And I only need to convert the kilometers. So for every 1 kilometer, there are 1,000 meters. And then for every 1 meter, there are 100 centimeters. And then for every 2.54 centimeters, there's 1 inch. And then for every 1 inch, for every 12 inches, there's 1 foot. And then for every 5,280 feet, there's 1 mile. We have 3 sig figs. I think it's 77.8 miles per hour. Is that right?
Yeah. But it tells us that,
Yeah.
kilometers is 16.
It does, but why I've said a couple of times in class that when you do this conversion, you're only allowed to do English to metric length by using that conversion. Why? Yeah, otherwise I'm going to have to start counting significant figures inside my unit conversions, and I don't want to have to do that.
You know the values from kilometers down to inches, you just skip them.
Nope. Because there isn't a conversion factor that says kilometers to inches, gives a conversion factor, and has the word exact after it.
I mean, kilometers to centimeters.
Oh, sure. Yeah.
No straight to that.
Absolutely, for sure. Okay, so you drop your iPhone in the river, but it's wrapped in a waterproof case that's supposed to float. The mass of the iPhone is 135 grams, and the mass of the case is 145 grams. What's the minimum volume of the case to get the phone to float? 180 would be okay, yeah. So why would 180 milliliters be all right? That's actually not quite good enough. 181 or 180.1 or 180.01? Why do I need just a little bit more volume? What's that going to do for me? And since the water's density is 1, I have to have it to be a little bit less than the density of water, and then it's going to float. If it's exactly the density of water, why is that not quite good enough? If you're in the Columbia River, what happens? Is the water nice and smooth? There's a lot of circulation going on, right? So if I'm something and my density is equal to water, I could get swirled around, and where would I be? Could be anywhere. It could be at the bottom, it could be at the top, it could be anywhere in the middle because my density is equal to that of water. I need it to be just a teeny bit less than that of water. So, yeah, you really should check to make sure that the volume is, and it's a little bit larger than the mass, and it's really easy to do. You just put it into like a tub, right, filled with water, and it'll float. I didn't do that. Somewhere there's a iPhone 3S in a perfectly sealed in a waterproof case somewhere in the Columbia. I don't know where, but if you find it, it's mine. Okay, what do you want to say here for this Greek theory and Dalton's theory? Why is this super important?
Because they're one of the first ones.
Okay, so why is that awesome?
Because they didn't have the tools to look at anything, they were just theorizing and it started the conversation.
That's the most important part, what you said last. It started the conversation. It gave them a jumping off point. It's you got to think about what was going on at this time. We were still not really super sure why people died when they cut themselves on a stick. And so to talk about the nature of everything being made out of atoms, then you can start doing experimentation and then understand what's going on. That whole, I'm just separating them and putting them back together is incredibly important for people who are actually doing separating and putting stuff back together. There was a great deal of chemistry that was going on during this time frame. It's just nobody knew what was going on. And once they decided that, oh, these things are all made out of atoms, and they realized that stuff was just moving back and forth, then it became easy to do lots of reactions and understand what was going on with them and apply them to other things. How about this next one about the magnitude of the two charges, about the proton and the electron? Their magnitude is definitely equal. The proton is like 2,000 times larger, but it doesn't matter. Its plus is exactly equal to an electron's negative. How about Dalton's answer to this? What happens during a chemical equation?
The connection between the chemicals is changed, or between the atoms is changed, but that.
Okay. Atoms. This is super short. I usually use, they combine, separate, and rearrange, but this is very succinct. What changes about the atom? Nothing. That's the super important part about Dalton. The atom is the atom. All I'm doing is hooking it up to different atoms or disconnecting it from atoms, whatever it is. I just change its connections. Why is Dalton super happy to know that water is H2O?
Because it has a perfect ratio.
It's got a nice ratio of 2s and 1s. And what else? Whole numbers, yep. Anything else?
It will always be.
It will always be H2O. No matter what, it's always H2O. How about this? Matter is mostly empty space.
you can say that the atoms are made up of empty space.
Okay, so the nucleus is about 10 to the negative 10th, or 10 to the negative 15th meters in size. So really, really small, right? And the atom is about 10 to the negative 10th meters. So the difference between those two things is 10,000, 5 zeros. So the nucleus is 10,000 times smaller than the atom. And where is basically all of the mass for the atom? In that dense nucleus. So what we're saying is I have a speck of mass in the middle, and the other 10,000 parts of the atom are just a bunch of empty space. That's probably the best way to put it. Okay.